Hello and welcome to our final lesson for this unit on regression analysis. This is a concept that if you've seen it before, you've probably seen it in a science class. Let me give you a little background. That's not what I wanted to push. Let's just say that I was to take a group of about 30 students and I was to collect data on their height and their shoe size. Okay, if I wanted to make a little graph to show what I collected in terms of my data. Let's say that I put their height as the independent variable down here on the x-axis, and let's say I put their corresponding shoe size over here on the y-axis as the dependent variable. Okay? If I went to a group of 30 random people and collected their height and shoe size, we would probably see something like someone who's shorter, has a smaller foot. I'm not even going to put any labels here, but let's just assume that it's just shorter to taller, right? And then this would be smaller shoe sizes to larger shoe sizes. Okay, so taller you get, the bigger your shoe gets, and maybe this isn't going to follow an exact line, and you might have some outliers here, but in general, if I was to make a scatter plot of the data collected from some people about their heights and shoe sizes, we would probably see an increasing behavior where the taller you are, the bigger your shoe is, right? So what we could do with data like this is regression analysis. We can create we can actually calculate an equation or a model that sort of represents this data. So, for example, in a science class, maybe you record data like this and you say, well, let me create a line of best fit for the data, if that's something that sounds familiar. So if I was going to create a line of best fit for this data, I would want a line to sort of capture as many of the points as possible, right? And then also have almost an equal number of points on either side of that line. So I think if I wanted to calculate a line of best fit or draw a line of best fit for this set of data, it might look something like that. So that line pretty well represents that data, right? And the purpose of this line of best fit would not be for data that we already know. What we would use it for is to make predictions of values that we don't, about values we don't know. So for example, let's say that this value right here, let's say that that's for someone who is 6 feet tall. And I know that that person who is 6 feet tall has a size 11 shoe. Okay? So based on the data I have, this 6 foot tall person wears a size 11 shoe. Fine. Well, what if I wanted to know the shoe size for someone who's 7 feet tall? Although my data stops here, my line of best fit continues, so I could go out a little further and say, okay, if I'm 7 feet tall, then what could I expect for my shoe size to be? And maybe based on my line of best fit, I could predict that the shoe size is like a 14. I don't know. I'm just sort of making these numbers up, right? But that's the concept, okay? So what regression analysis does is it takes a set of data and it tries to calculate a mathematical model to represent that data. Now I showed you one where it's sort of linear, but it doesn't necessarily have to be, and we'll talk more about that in just a second. Okay, so regression analysis is the process of estimating the relationship, trying to estimate the relationship between variables in a data set. So you're looking at two different values and what's happening. Are they increasing linearly? Are they decreasing linearly? Is it sort of a parabolic or quadratic relationship between the data? Let's try to estimate it mathematically using this process called regression analysis. So when your data appears to follow the pattern of a specific function, then we can calculate a regression equation, or sometimes we call it a regression model, in that format. And the purpose of the regression model is not for data that we know, but it is to make predictions. It's used to make predictions for unknown values, right? So the 7 foot person, how big's their foot going to be? Or if I knew someone had a size 14 foot, could I, sort of use my regression to predict how tall that person would be? Okay. Now I could take any data set and calculate any type of regression. So I could take any data set and calculate a quadratic regression. I could take any data set and calculate a linear regression. That doesn't necessarily guarantee that that's going to be a good model. So let me go back to my data here. Okay, let's say I put this data into a calculator, and we'll talk about the steps shortly, but let's say I asked it to calculate a quadratic regression. So it could use this data and calculate a quadratic function to try to match with that data, but is it parabolic? Not necessarily, right? So I can ask the calculator really to do anything. That doesn't guarantee that the model it spits out for us is going to be a good model. So how do we know if the model is going to be good or not? How do we know if our regression analysis is accurate? Well, we have to look at something called correlation. So correlation is used to determine the strength of the relationship. How strong is the relationship? Not only how well do the points correlate to one another, but how well do they correlate to the model that you're calculating, the regression model. So it's going to tell you how accurately your model can be used to make predictions. If you get a strong correlation to your model, that means the model pretty well fits your data, and it would be used to make pretty accurate predictions, and vice versa. If it's a weak correlation, then it's going to be a weak predictor. Okay, so to judge the correlation, we're going to be looking at the value of r or r squared. So r squared is typical. We're going to use r if it's linear, but r squared in any other case, but they sort of represent the same thing. Okay, r is the variable that we will use to measure the correlation. We call it the correlation coefficient. R squared, or r, will always be a value from -1 to +1. So think about a scale from -1 to +1, right? If we had a scale from -1 to +1, still on pink here, that's okay. -1 to +1, where 0 is in the middle. Think about these as percentages, okay? This would be like 100% here. If you calculated an r squared value or an r value of 1, it's like 100%. That would be the strongest possible positive correlation that you could have. That means your points are exactly on that model, okay? And if you were like maybe a 98% or a 75%, what happens is as you get farther away from 1 or you get closer to 0, 0 would be no correlation at all. That means you asked your calculator to calculate the model, but those points, they're not correlated, right? They're not all increasing or decreasing with regards to that model at all. So even though you asked the calculator to do it, this model is going to be weak for making predictions. And then the same thing is happening on the other side, where -1, it's weird to think about a -100%, but this would be the strongest possible negative correlation. Okay, this is negative correlation here. So positive correlation was like we saw with heights and shoe sizes. The points would sort of be increasing, so that would be a positive correlation, where if you had a negative correlation, then you would have values that are still correlated, but they are decreasing in nature. So if you had a +1, r equals a +1, that's the best case scenario for a positive correlation. That means you'd be looking at a graph where all the points were lined up exactly. Okay, and if it was the strongest negative correlation, right, strongest negative means again they're going to be lined up exactly, but they're just decreasing. Okay, and the closer you get to 0, or the farther you get from -1 or +1, the weaker the correlation is. Okay, so closer to 0 implies a weaker correlation, and then closer to -1 or +1 implies a stronger correlation. And if you are 1 or -1, that is the best case scenario. Okay, so now how do we go about calculating regression, and how do we determine what model is going to be best? So I'm going to show you how to do this in Desmos, and let's write down a couple things, and then I'll actually model it for you. So from the graphing screen in Desmos, you're going to click the little plus sign that's in the upper left hand corner, and that's going to allow you to add a table so that we can enter our data. And then in the next line, you're going to type in the regression equation, or the model. Those are sort of interchangeable words here. The equation or model that you want to calculate, and it should be appropriate for the data. So if you're looking at data that looks sort of like a parabola, you're probably going to want to put in a quadratic regression. If you have data that's linear, maybe you want to put in a linear regression. But it's going to be important because sometimes we can't extrapolate the data very far to actually look at the correlation values. What we're going to want to do is calculate multiple types and see which produces the strongest correlation. Okay? Now we can calculate regression models of just about any type. So it can be linear, quadratic, cubic, so all those polynomial functions we've seen in our parent function section. It could be a square root, it could be a cube root, it could be absolute value, it could be whatever kind of function you can imagine, okay? But there are three that are pretty common that pretty typically can encompass the data that we're going to be looking at. So we're just going to focus this lesson on three common types of regression. So if it's a linear regression that you want to calculate, linear regression, so a line, I'm going to go back and forth here. A line is typically in this y equals mx plus b format. So that's sort of what we're looking at here, but when we calculate regression, we're still going to have the y, and then we don't want an equal sign because we don't necessarily have exact data. So in place of the equal sign, we're going to put the tilde is what that's called, and then we still want m, x, and plus b. So that's what our equation will basically look like, except when we add our table in Desmos, in the table it's going to call this x1 and y1, and we want to make sure that our model is connected to this data, so we're going to call this x1 and y1. Okay, and then it'll be similar for a quadratic. Standard form for a quadratic is ax squared plus bx plus c. So we're going to put the y, we're going to put the tilde instead of the equal. We're still going to have this ax squared plus bx plus c bit, but I want to again make sure that it relates to my data. So I want to call these x1s, and I want to call this y1. Okay, and then lastly we have exponential. So exponential, remember, was the variable exponent, and technically we're going to put a coefficient here. So a b to the x power. Let me rewrite this a little bit nicer. So a b to the x power, this is like our standard form for an exponential. In our transformation section, remember we looked at 2 to the x power as an exponential. Same concept here, okay? And we want, again, to relate this to the data that's in our table, so we'd call that an x1 and y1, and we would replace the equal with a tilde. All right? So to calculate linear regression, we would type in y1 tilde m x1 plus b, and those are subscripts, but when you're typing them into Desmos, if you just hit x and then the number 1, it will automatically subscript it, so that's kind of nice. For quadratic, it's going to be y1 tilde a x1 squared plus b x1 plus c, and then to type in, or to calculate exponential, we would type in y1 tilde a b to the x1 power. Okay, so we're going to see how this looks. I'll show you exactly what you're typing into Desmos, and we're going to try to, for these first three examples here, determine which one of the models would most closely align. So anytime we're well, for the purposes of what we do here, and just to practice with these three types of models, when you're calculating regression, you actually want to calculate all three, compare the correlations for all of them, and then you choose the model that has the strongest correlation. Okay, so here's Desmos. You see the little plus sign, so I'm going to hit the plus sign, and then I can add a table, and I want to type in my data. So 1 and 5, and maybe you can go a little faster than me, 11, 15, 20, 25, and be really careful because you miss one number and then all your calculations are going to be off from there. Okay, so 3, 12, 15, 24, 35, 39, and 50. Okay, so there's my data. And if you look on the graph, you can see a couple points there. If I want to see all of the points plotted, it's actually plotting those points as I put them in the table. In the blue bar on the side here, there's a little, looks like a magnifying glass with a plus sign. If you tap that, it's like an auto zoom. and I had did it twice there, but it will automatically zoom out so that you can see your data. Now to me that data looks pretty linear, but I'm going to calculate each type of regression so I can guarantee that I'm going to get the best model for it. So I'm going to type in linear first. That's going to be y, and then to get a subscript of 1, I'm just going to hit number 1 next, and it's going to automatically subscript it. And then tilde, I have to go into my keyboard and get the little tilde in the bottom here. And then I want m, x, and again I'm going to hit the number 1 to subscript that, and then a plus, and then I got to go back here and get b. And there it is. Now what you see is a couple of things. So you see your r squared and r values here. These are correlation coefficients. For linear, we want to look at r, and at 0.9922, like that's almost 100%. That's pretty darn good. Okay, so this is a strong correlation for our linear model. And to write the linear model, then we would use the m and the b that's calculated there. Okay, now I just want to be sure that it's the best one. So let me calculate my other models and look at their correlations as well. So I want y, 1, again a tilde, a, x, 1, and then I'm going to square that. Looks weird, huh? Subscript and a superscript. Plus b, x, 1, and then plus c. And there's that one. Okay, so there's r squared at 0.98, so still a pretty strong correlation. It would still be a good model for making predictions, but 0.98 is not as strong as 0.99. Okay, so far the linear one is in the lead. Now let's try the exponential. So y, 1, tilde, and then a, and then parentheses, b, and then raised to the x1 power. Alright, so there it is, r squared at 0.9115. And 0.9115, that's still a pretty strong positive relationship there, but neither the exponential or the quadratic was as good as the linear. So I'm going to go back because the linear had the strongest correlation. We're going to say that this is linear. And the correlation we calculated at 0.9922. That's a strong positive correlation. So if it's linear, we want our model, remember our model is supposed to be a y equals mx plus b type of deal. Well, it's telling me here what m is and what b is. Let's see at the bottom of the list there. So our model for this situation is going to be y equals about 1.96x, and we're going to add b, which is 1. I'm going to just say 63-ish. Now the more you keep on the decimal, the more accurate it's going to be for making predictions, but just to get it on paper, I think rounding to, the hundredths place is going to be sufficient. Okay, so there's that. Now we get to do this again. Now I don't want to have to retype those models in every single time. So I'm going to leave all 3 models in here for this entire activity, and all I'm going to do now is just delete the data out of my table and retype in the data. It's just going to be a little more efficient than having to retype those models every time. Alright, so now new data. 0, 2, 3, 4, 5, 7, and 10. And then over here, 3, just kidding. 3, 8, 13, 18, 11, 4, and 1. Now, looking at, again, I'm going to hit the little plus sign just to zoom this a little bit better. The data appears to be going up and coming back down. I think just by looking at the data, it's probably going to be parabolic. But let's look at the 3 models. So a negative correlation for linear, negative 0.3. That's kind of weak. R squared, quadratic. Let's see, 0.66. So it's a little better, maybe like an average correlation. And then 0.05, that's terrible, okay? So definitely quadratic is going to be the best for us here. So remember our standard form for our quadratic is ax squared plus bx plus c. And now it's giving me values for a, b, and c at the bottom of that quadratic regression. So this is going to be quadratic. And you know what? Let me just change colors here so it doesn't blend This one is quadratic. And we have r squared at about 0.66. 0.6641. Squeeze that in there. Okay, and that is that's, you know, it's a decent, it's not the strongest possible, but that's like an average positive correlation. And so our model is going to be y equals, in place of a, we're going to put in negative 0.43. So negative 0.43, and then that's in front of our x squared, plus b in front of x, and b is about 3.78. 3.78 in front of x, and then we're going to add in c, which is about 3.94. 3.94. Okay? And now we've got one more, and you could probably just guess what's going to happen. I don't know what I did here. There we go. What's going to happen on the next one, since I'm trying to show you all three models. But let's delete this data out. Don't want to retype all those models, just want to retype my data. Okay, so we've got 1, 2, 4, 6, 8, 9, and 12. And then 1, 5, 17, 20. That's not 20, that's 70. 270. This data's starting to grow really fast. 504, and then 4100. Okay, so I can see here what is going on. I don't know where all these extra lines came from in here. I did something to my calculator. What did I do? Everything still looks okay. Okay, so I'm not sure what's going on with my screen. I moved something and I messed with something, but I can still see what's going on with the information I need. So my linear model, which maybe I just need to zoom. Hang on. There it goes. Just zoomed fixed. Okay, that was bizarre. So my linear model has a 0.7433 correlation. Not too bad. Quadratic, 0.9282 is pretty good. And then our exponential has an r squared of 1, which is an exact match. That means that is the perfect model for this data. Okay, so we had an exact match here. This doesn't get any better than a correlation of 1. So this is definitely going to be exponential. We had r squared equal to 1. This is best case scenario. So our exponential model is going to be a b to the x power. We're just going to replace the a and b with what it gives us for a and b. So we're going to say y equals a is about 1.01, and then b is about 1.998. I'm going to keep more decimal there just so I don't have to round that to 2, and then to the x power. Okay, and there it is. All right, so now that we've got a little practice under our belts, just calculating the regression itself. Remember, the whole point of this was to be able to use the regression to make some predictions. So that's where we're going to be headed next. Let's try to use this concept of regression, this regression analysis, to make some predictions. So once you have your regression model calculated, what you want to do to calculate a specific x value, if they tell you x equals 9, what's y going to equal? Well, you're going to type in the y equals number they give you, and then look for an intersection to find the x value that corresponds with it. And I'll show you an example in a few minutes. So if I want to calculate a y value, I'm going to type in the given x equals into a separate line, and again, I'm going to be looking for an intersection. Okay, so I'll show you. Let's look at this first problem. So I got all my models in here. Gosh, keep moving my table. Let me get rid of my data. Okay, so new data. We have the heights and shoe sizes of a dozen random women collected and organized into this table. So we have 60, 62, these are obviously inches, 65, 66, 59, 64, 65, gotta move, 62, 60, and 61. Okay, I now move my calculator again. 6, 5, I can't imagine having feet that small. 7.5, not that I have huge feet, okay, we're like a 7.5, just wanted to throw that out there. 8.5, nobody cares. 4, 7, 8, and then 7.5, 5.5, and 6. Okay, so now we've got all of our data in there. Let me hit my zoom button so I can see it all. Okay, so there it is. Just looking at the data, kind of hard to tell what's going to match best there. So let me look at my correlation coefficients here. For linear, R is about 86%, quadratic 75%, and exponential 75%. So we're going to go linear on this guy. Okay. Now I'm going to delete these out just because it's going to clog up my screen. So let me just go with my linear model. So this is going to be linear because it had the best regression or correlation, which was 0.8669. So the model is going to be y equals 0.51, let's just say about 0.51 in front of x, minus 25.04-ish for b. Okay, so there's our model. Now, I could actually use the model on paper and try to do some calculations for predictions without Desmos, but Desmos is going to hold all those decimals in there, so I don't have to do any rounding. So if we look at part B says to predict the shoe size of a woman who is 6 feet tall. So we have heights here, which are x values that we put into the table. We have shoe sizes here, which were the y values that we put into the table. Okay, so when it says to predict the shoe size, that means we're looking for a y value, and it says predict that shoe size for someone who's 6 feet tall. So 6 feet tall means they are what height? Well, in the table, the heights are in inches, so 6 feet tall is 72 inches. Okay, so I want to know a y value that corresponds with an x value of 72. So here's what I'm going to do. In Desmos, so I have my table of values, I have my regression, I'm going to go to another line here, and I'm going to type that x value in. I'm going to put x equals 72. And x equals 72 is a vertical line at 72. I'm going to zoom out so you can see it. So that purple line, there's x equals 72. If I find where that purple line intersects my regression model, then I can see the y value that corresponds with that x value of 72. So in Desmos, it shows me there that when x is 72, the corresponding y value is 11.353. Okay, so now what does that mean? Well, that means that if, based on the data here, if we wanted to make a prediction with that regression model, if a woman was 6 feet tall, she'd probably wear like a size 11 or 11.5, right? 11.353 doesn't exist as a shoe size, so she'd probably wear, probably wear an 11 or an 11.5. Okay, not so bad. And then we're going to do the same thing on the next one, but we're working in reverse here. This next one says to predict the height. Heights were x's. This time we don't know the x value. When there's a shoe size, or she wears a shoe size of 9, that means y is equal to 9. So let me go back here. This time I'm going to get rid of that x just because how I keep moving these things around. I'm going to get rid of the x value. The nice undo button. This is what's saving me. So get that one out of there. Okay, so now in the next line I'm going to put in what I know this time, which is I know that y equals 9. Y equals 9 is that black horizontal line that popped up on the screen. And again, if I just tap on the intersection with that in my regression model, it tells me, gives me the coordinates there, at 67.343, comma 9. That tells me that shoe size of 9 is probably going to be someone that's about 67 inches tall. So she's likely about 67 inches tall. It's like 6'7". Okay, there it is. Not so horrible. Now, I want to set up for my next problem. We're going to try this once more. And I don't want to retype those models in here, so let me go back to my undo button. Undo, 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 until I get those other models popped back into my screen. And everything's there. Good. See? Undo button. You gotta love the undo button. Alright. Get rid of that for a second. Okay, so let me go back here. The following data for this problem represents the number of goods in billions that are exported from the United States. Now, if you notice, the years are actually given in years, and then in the little sentence below the table it says, let X be the number of years after 1998. That means we don't actually want to type those years in as X values. So the X values that we're going to type in should be how many years after 1998 we are. So after 1998, this would be 0 years after that, because it is the year. This would be 3 years later, 4 years later, 5 years later, 6, 7, 8, and then 9 years later. Okay, so that's generally how problems will work with time. If you're given the times in years, you usually start with the initial year being year 0 and type those numbers in, just because you'll skew the numbers in your equation if you use those big years as values. Okay, so Y is the number of exported goods. That's going to be fine. So we're going to type this new data in. That means we got to get rid of the old data. Out with the old, and soon to be in with the new. And somehow I moved that. I don't know how I keep doing this. Whatever. I'll fix it in a minute. It's because I'm not working on a full-size thing here. Okay, I'm making excuses for myself. Alright, so we have 0 years after 1998, and then we've got 3 years later. And then 4, 5, 6, 7, 8, and I think we went to 9, didn't we? Yeah. Okay. So 231.1, 201.3, which was supposed to be here. 151.4. 147.9, 133.9, 127 something, 4, 121.5, and finally 118.7. Okay, so data's in, and linear, we're at a oh, let me zoom on my data real quick. Yeah, trying to guess based on the data. Probably not the linear. Hard to see which one's going to line up best with those, whether it's going to be quadratic or exponential. Well, let's just take a peek. Okay, so linear, we're at negative 0.95. That's a pretty strong negative correlation. Quadratic is 0.94, so linear was better there. And the exponential is 0.93, so it looks like the strongest is our linear again. This is crazy. Negative 0.94. Tough to say if we should use the linear or the r² value there. Oh, we're gonna go linear. Okay, so again, maybe. Oh, I hate to lie to you guys here. I kind of wanted you to see another example, but it's fine. They all work the same way. You pick your model, okay? So this is going to be linear again, because it has the strongest correlation. In this case, negative 0.9491. And that's a stronger negative correlation than this one is positive, or than this one is positive, okay? So we're going to keep the linear. So our model is going to be y equals, slope is a negative 13.27-ish in front of x, plus b is 223.84. Okay, and now we're going to use this to try to make some predictions. So part B, it says predict the number of goods. Now remember, these years after 1998 were x values and the goods were y values. So when it says predict the number of goods, that means to find a y value in 2013. Well, 2013 would be how many years after 1998? 15 years later, so we're going to put x equals 15 in there. So let me go back, and I'm going to leave. Okay, I just keep moving stuff around. Alright, let me get rid of this quadratic, because I don't need that anymore. Get rid of that one. So linear model's in there. Now, I know x equals 15, so I'm going to type that in, x equals 15, and it's going to be a vertical line there, and if I find the intersection at 15 and 24.729, then I can see that in 2013, or 15 years after 1998, the number of exported goods is going to be about 24.7 billion. So about 24.7 billion exported goods. And I stuck the billion on there because it says up here that it's in billions. Oh, it also tells us right there. Okay, one more, same concept. Let's see, it says in this last part, predict when. That means we're going to be looking for an x value when the number of exported goods is going to decrease to 50 million. So the exported goods, the y, is 50. Okay, so back to my calculator. This time, get rid of that y you're in there. Okay, so this time I'm going to type in y equals 50. And there's a horizontal line, and I'm going to find where it intersects with my graph. So I can see that intersection at 13.096 and 50. Okay, which tells me about 13 years after 1998. 13 years after 1998, or in the year, what year would that be? 13 years after 1998. That would be 2011. Okay, there it is. So that's your regression analysis. Give it a shot. I try to leave pretty good feedback in your practice assignment, so if you're struggling with something, when you get an incorrect answer, it should pop up with some pretty good work. But if you're struggling, as always, I'm here to help. So just shoot me an email and I'll do my best. Or text, phone call, whatever. Come to my conferences. I've been pretty lonely in there. Otherwise, if you're doing good, work through those practices, and then your module quiz is going to be due shortly. Okay, so make sure you're paying attention to those due dates. All right, guys, take